Hello and thank you for watching. We are Innovative Global Solutions, an enterprise with the initiative of creating low-cost solutions for developing countries around the world. Today we will be presenting on our three projects: the Vaccine Transport Unit, the Infant Incubator, and the Integrated 3D Printer for Sustainable Future. Before we get started, we would like to take a moment to acknowledge our advisors, Dr. Manser and Dr. Tawari, for their continued involvement in the team in the pursuit of its goals. Additionally, the Enterprise team would like to thank General Motors for offering their sponsorship, and specifically Jason and Blake for their advice during the building and testing phases of the project this spring semester. We will be highlighting our capstone project, the Vaccine Transport Unit, which addresses the issue of excessively low vaccination rates in some rural, underdeveloped areas. Vaccines are necessary for the prevention of many serious diseases, but have a strict temperature requirement of 2 to 8 degrees Celsius to prevent them from denaturing. Our target area of northern Nigeria has extremely low vaccination rates due to inefficient cold chains as indicated in the figure shown. Vaccines are transported unrefrigerated over rough terrain, with the total time until they are administered reaching up to 30 hours. Administered denatured vaccines will be ineffective, causing communities to lose trust in vaccines altogether. Therefore, our primary design requirements were to develop a vaccine cold transport unit that is capable of keeping vaccines within a 2 to 8 degree temperature range for a minimum of 30 hours.
Competing vaccine containers lack sufficient holdover time, efficient vial extraction, and a temperature monitor, which we focused on. Each prototype used phase change material, also known as PCM, which is a substance that releases energy for cooling properties when melting to its specified phase change temperature. Prototype 1 had various lids to minimize vial exposure. However, this decreased our temperature retainment results. Prototype 2 was increased in size, allowing for more PCM. However, the temperature constraint was still not met. Prototype 3 experienced a design makeover where the vial sleeves allowed for efficient vial extraction, and the type of thermal insulation was changed. These design changes have allowed Prototype 3 to exceed competing products.
Our team's comprehensive design excels where other containers on the market are limited and at a developmental cost 54% less than competitors' retail price. The foam vial sleeves provide protection and accessibility for the glass vials. The removable phase change material provides cooling in a specific temperature range. The internal division system compartmentalizes components and provides structure for the onboard temperature monitoring system. The combination of vacuum insulated panels and foam aerogel provide the insulative properties necessary to reach the holdover time requirement. Additionally, a backpack form factor makes the unit easily transportable on foot or by motorcycle.
Our vial sleeves have three main advantages, the first being improved vial protection. In the previous prototypes, the vaccine vials directly exposed to the insulation. With our new design, the vials are surrounded by foam sleeves to ensure the vials are thermally and physically protected. Next, there's increased capacity. Previously, we were only able to fit 50 vials, and we have increased capacity to 52 vials, or 520 dosages, with multiple foam sheets and an efficient design layout. Lastly, there's improved accessibility. Before, it was difficult to remove the sleeve from the container and remove the vials. The new design allows for easier access with less vaccine vials exposed at a time.
The biggest improvements made from last year's design was the addition of the printed circuit board and upgrading the microcontroller to a TNC. Adding a PCB allowed the design of the sensor system to be smaller and more reliable due to the reduction of wires. Adding the TNC and implementing changes to the code made the battery life better than the previous design by a little over 300 hours. The previous design's battery life was 32 hours, whereas the current design's battery life was an estimated 350 hours. Some of the other features that were included in the design was the alarm system to notify the user when the temperature of the vials are outside the 2 to 8 degrees Celsius, and the external battery pack so changing out the batteries is quick and easy.
To meet our temperature and time constraints, two main features were changed: the location of the PCM and the R value of the insulation. The R value is a measure of how well a type of insulation resists the conductive flow of heat. Prototype 1 had the PCM in the center of the container, which was surrounded by extruded polystyrene, having an R value of R6. Our constraints were not met, so Prototype 2 used more insulation and PCM. However, this did not change the outcome. Prototype 3 experienced a design makeover where vacuum insulated panels were used, which have an R value of R25. Additionally, the PCM changed location to the outside of the vial sleeves. These design changes have allowed Prototype 3 to meet our constraints.
Shown in this figure are the holdover test results for 3 temperature probes for each of the 3 prototypes that were made throughout the course of the project. As you can see, prototype 1 held a temperature range of 13 to 15 degrees Celsius for 9.6 hours. This was unsatisfactory because the temperature range was outside of the required 2 to 8 degrees Celsius, and the holdover time was significantly below the minimum 30 hours. Prototype 2 held a temperature range of 11 to 14 degrees Celsius for 29 hours, which also did not meet either requirement. Prototype 3 had a holdover time of 46 hours where all 3 probes were within the allowable 2 to 8 degrees Celsius temperature range at the same time. This exceeded our design requirement by 16 hours. This figure shows the results of the holdover test conducted on prototype 3. As shown in the figure, the ambient temperature of the testing room averaged 25 degrees Celsius. Probes 1, 2, and 3 held steady-state temperatures of 7.7, 6.7, and 4.8 degrees Celsius, respectively. Probe 1 had the highest probe location in the container, and Probe 2 had the lowest probe location during testing. Next, we will discuss the infant incubator and integrated 3D printer for sustainable future projects that our enterprise is also working on.
The infant incubator is a brand new project here at IGS. So why does the world need a low-cost infant incubator? Well, between 2020 and 2030, 52 million children under 5 are estimated to die primarily from premature birth and low birth weight due to the lack of access to care. Infant incubators provide environmental control to support the infant's growth, reducing infant mortality rates. Unfortunately, there are no low-cost infant incubators available on the market. Our incubator will have a low-cost, low-power design that focuses on modularity for easy maintenance. This idea of modularity is beneficial in the event that a subsystem breaks down because it can easily be replaced with a new module. The incubator's subsystems will consist of temperature control, humidity control, and vitals monitoring. Temperature and humidity control are extremely important as a premature infant needs a precisely controlled environment to promote growth as well as lower the risk of infections and diseases. Our vitals monitoring system will be designed to constantly check vitals such as heart rate and SpO2 to verify that they are within a safe range. If they are not, the incubator will immediately notify the caregiver. This semester, we are focused on researching and designing an incubator. On the slide, you can see the initial design. At the beginning of next semester, we will begin ordering supplies and equipment to start building the first prototype.
The integrated 3D printer for sustainable future is essentially a 3D printer that shreds plastic waste, melts it down, and prints out useful products for needy communities. This project was initiated to help curb the growing issue of plastic waste accumulation in lower-income countries. Unfortunately, there is a staggering correlation with the lack of clean water in developing countries. Plastic water bottles are a life necessity to these populations. Therefore, a lot of these developing countries struggle to keep up with plastic waste management. So, IGS hopes to create a recycling printer that not only prints with high resolution, but is also fully open-sourced, portable, and low in cost to accommodate the people that really need a solution like this. So far, engineering students on this project have been ideating different methods to achieve these goals, such as direct material extrusion, portable and collapsible frame designs, and international user interfacing techniques.
Thank you for watching our presentation on our 3 current projects. If you want more information on our projects, please check out our website at the URL shown. Or, if you have any questions about our projects or want to get involved, please contact us by email at igsenterprisemtu@gmail.com.